stable as a rock. We've all heard that saying, right? People use it for things that are solid, dependable, unchanging.
Yeah, absolutely.
Yeah.
But, when you look at Earth's history, the big picture...
Rocks are anything but stable.
Exactly. They're constantly changing, breaking down, reforming. It's this endless process, the rock cycle.
And that's what we're diving into today. We're going to unpack this whole rock cycle thing.
That's right. Using the material we have, we'll explore how those three main rock types we always talk about, igneous, sedimentary, metamorphic, how they're all connected.
And the forces behind it all. This is basically your shortcut to getting a core geology concept.
A fundamental one, definitely.
We've talked about those rock types before, but seeing them in the cycle, well, it just clicks, doesn't it? You see how they relate dynamically.
It really brings it to life, like
Yeah.
watching the Earth constantly remake itself.
Totally. So our mission today is pretty clear. Why are surface rocks always changing? Why do we tend to find younger rocks more often at the surface? And crucially, how does this whole cycle fit into the bigger Earth system picture, especially plate tectonics?
Okay, yeah, let's get into it.
So the rock cycle, it's not just one simple loop, is it?
No, not at all. It's much more like a network, a complex web of paths. Different rocks form in different places, different geological environments,
Like the ones in the geology at a glance sections.
Exactly, those. And the cycle shows how material moves between these environments. Figure C.1 and the resources, it maps this out visually. Lots of arrows showing the different routes.
And some of those routes are pretty wild. Like
Yeah.
you start with igneous rock, right?
Yeah.
Formed from cooled magma.
Solidified melt from the mantle, yeah.
And then bam, weathering, erosion, breaks it down into sediment.
Wind, rain, ice, just grinding away at it.
Then that sediment gets buried, squashed together, lissification, that's the term.
And boom, you've got sedimentary rock.
But wait, there's more. That sedimentary rock could get buried even deeper.
Yeah, way down. Intense heat, immense pressure.
And it changes again into metamorphic rock.
But here's where it gets really interesting. The cycle can kind of loop back. That metamorphic rock, if it gets hot enough.
It melts.
Partially, yeah.
Yeah.
Creates new magma.
Hmm.
Which then cools to form? Guess what?
New igneous rock. Back where we started almost.
A complete circle. Igneous up sedimentary, metamorphic, igneous again. But that's not the only way it can go, right?
Oh, definitely not. It's full of detours. That metamorphic rock, for instance, it doesn't have to melt.
Right. It could get pushed back up to the surface
Uplift it,
and then eroded again, creating new sediment.
which forms new sedimentary rock. So igneous to sedimentary to metamorphic and then straight back to sedimentary. That's a path.
Or the original igneous rock could just get buried deep and heated up directly.
Skipping the sedimentary step entirely.
Yeah, becoming metamorphic rock right away. And then maybe it gets uplifted and eroded into sediment. Exactly. Or even sedimentary rock itself, you just get uplifted, eroded, and turned back into more sediment.
Which makes more sedimentary rock. It all depends on the journey.
Precisely. These paths, they tell a story. A rock's geologic history, what conditions it faced over millions, maybe billions of years. Incredible timescales.
It really makes you think. So to make this less abstract, the material gives us a case study, right? Starting with like a hotspot volcano.
Yeah, a continental hotspot. Think Hawaii, but maybe on a continent. Magma comes up from the mantle, erupts, cools into basalt, igneous rock.
Okay, so we've got our basalt. Now what?
Now it just sits there, exposed. Wind, rain, plants start working on it, breaking it down physically, but also chemically changing minerals into clay.
Ah, the weathering process.
Yep, and you've seen this happen, rivers turning brown after rain.
Yeah, full of mud.
That's often clay, washed away. So in the case study, this clay gets carried off, maybe by rivers, and dumped somewhere else, like the edge of a continent. Let's call it continent X.
Okay, deposition at the continental margin.
Right. Layers of mud build up and build up. Gets buried under maybe 6 kilometers of other sediment in this example.
That's a lot of weight.
It is. And that pressure squeezes the water out, compacts the mud, lidifies it, turns it into shale, sedimentary rock.
Got it. Basalt to clay to shale. But the drama's not over.
Not by a long shot. Now, imagine continent X slams into another one, continent Y.
A continental collision, like India hitting Asia, creating the Himalayas.
Exactly like that. Mountains get pushed up. And that poor shale, which was near the surface, relatively speaking, gets dragged way, way down in the collision zone, maybe 30 kilometers deep.
Oh, what happens down there?
Intense heat and pressure. It completely transforms the shale.
Yeah.
The minerals recrystallize, align themselves. It becomes schist. A metamorphic rock. You can see this sequence in figure C.2.
Shale becomes schist. Metamorphic. Okay, then what? Mountains don't last forever.
True. Erosion starts attacking the mountains as soon as they rise. Wind, water, ice wear them down, and eventually some of that deeply buried schist gets brought back up to the surface.
Exhumation, like digging it up, but naturally.
Kinda, yeah. So now the schist is exposed, and guess what?
It starts eroding too.
You got it. Breaks down into new sediment, rivers carry that away, deposit it somewhere else, bury it, and you can get new sedimentary rocks. Sandstone, siltstone, maybe even more shale.
Wow. So the metamorphic rock becomes the source for a new sedimentary rock.
It can, yeah. Though some schist might stay buried, of course.
Okay, is that the end of the story?
Not quite. There's another twist.
Yeah.
Imagine later on, things change. The crust where those old mountains were starts to stretch and pull apart.
Continental rifting, like the East African rift.
Exactly. The crust thins, breaks, and this allows hot magma from the mantle to push its way up again.
Oh, and more heat.
A lot more heat, enough to actually start melting the schist that's still down there.
So the metamorphic rock melts.
Partially melts, yeah. And this creates a different kind of magma, usually richer in silica felsic magma. It's less dense, so it rises.
And if it reaches the surface or cools near it,
It forms rhyolite, another igneous rock, but different from the basalt we started with, and boom, we're back to igneous rock. The cycle's completed a loop, in a way.
basalt to shale to schist, then maybe partially melted to form rhyolite? That's quite a journey.
It is, and a key thing to remember, like the material points out, is the atoms themselves are getting rearranged constantly. That silicon atom in the basalt's pyroxene,
Yeah.
it could end up in a clay mineral in the shale, then maybe a mica crystal in the schist, and finally part of a quartz crystal in the rhyolite.
So the atoms don't stick together. They get shuffled around.
Totally shuffled. Erosion and transport spread them all over the place. It really shows how dynamic this whole thing is. The Earth is just constantly mixing its ingredients.
It really is. Now, okay, we know this cycle is always happening, but it's not all at the same speed, is it? Things must happen at different rates.
Oh, vastly different rates. That's why we find rocks of all sorts of ages at the surface. The material gives a great contrast. You've got some Precambrian chert beds,
Ancient stuff.
billions of years old,
Mm.
and they've basically sat there unchanged. That's an incredibly long time for those atoms to stay put in that rock.
A very long residence time.
Exactly. But then you look at somewhere like the Appalachian Mountains. Geologically active region, relatively speaking.
Been through a lot.
Oh, yeah. Ocean basins opening and closing, mountains building up, rifting apart. The rocks there have probably been through multiple rounds of the cycle in just the last few 100 million years.
So some rocks are like tortoises, others are like hares in this geological race.
That's a good way to put it.
Hmm.
And this case study we walked through, it focused on continental rocks. What about the ocean floor? Is the cycle different there?
Good question. Continents get eroded a lot, right? Create sediment.
Right, and continental crust is relatively light, buoyant, so it mostly stays up top. It doesn't really get subducted back into the mantle much.
Mostly avoids being recycled that way.
Yeah, though some sediment washed into deep ocean trenches can get dragged down,
Mhm.
and maybe bits of the deep lower crust too. But generally, continents stick around.
Okay, so oceanic crust. It's mostly basalt and gabbro formed at mid-ocean ridges.
Yep, and it's covered by water, so it doesn't get weathered by wind and rain in the same way continents do.
So less erosion, less sediment formation directly from it.
Generally, yeah. It doesn't really follow that classic sedimentary path via surface weathering, quite like continental rocks. Its main story is creation at ridges and destruction at trenches.
Ah, subduction. That's the key for oceanic crust recycling.
That's the main mechanism. As it sinks back into the mantle, it gets heated up, put under huge pressure. It metamorphoses. Basalt turns into denser stuff like eclogite.
And does it just disappear into the mantle?
Most of it does, yeah. Gets carried deep down. But some of it might melt as it goes down or cause melting above it.
Which could create magma for volcanoes above the subduction zone.
Exactly. Like the Andes or the Cascades. So some material gets recycled back into new igneous rocks that way. But the bulk of the oceanic plate goes back into the mantle.
So distinct cycles for continental and oceanic crust, broadly speaking. Okay, we've seen the paths, the rates, but what's the engine? What actually drives the whole rock cycle?
Fundamentally, it's because the Earth is so dynamic. It's not static. You've got all these different rock-forming environments we mentioned.
And what keeps things moving between them?
Two main things. Earth's internal heat from radioactivity and leftover heat from formation and gravity. These power plate tectonics and those mantle plumes that cause hot spots.
So plate movements are key.
Absolutely central. When plates collide, you get mountains. Uplift exposes rocks to erosion, creates sediment. Collisions and subduction cause metamorphism and melting, generating magma.
Makes sense.
When plates pull apart, like in rifts, you also get magma rising, and you form basins where sediments can collect.
Hmm.
Plate interactions are constantly creating the conditions for rock transformation.
So that's the internal engine. What about forces on the surface?
That's where external energy comes in, mainly heat from the sun, plus gravity again.
How does the sun drive the rock cycle?
The sun drives the weather, doesn't it? Wind, rain, ice formation, ocean currents. These are the things that cause weathering and erosion at the surface.
Ah, the agents that break rocks down and move sediment around. The sedimentary part of the cycle.
Exactly. And we can't forget life,
Life plays a role.
a big one. Think about oxygen in the atmosphere, mostly from plants, right? Oxygen is crucial for certain types of chemical weathering. Plus, organisms directly break down rocks, physically and chemically. Tree roots, burrowing animals, microbes.
Right, biological weathering.
So putting it all together, the rock cycle is powered by this amazing combination of the Earth's internal heat, solar energy from outside, gravity acting on everything, and even life itself. They all work together to keep things moving, reacting, changing.
It's a truly interconnected system, which brings us to this idea of cycles in the broader Earth system. The rock cycle isn't alone.
No, definitely not.
Yeah.
And a cycle generally just means a series of linked events that repeat. The material makes a useful distinction, though. You have temporal cycles, like
Like the seasons or phases of the moon.
yeah, time passes, things repeat, but the actual stuff involved doesn't necessarily move around or change form dramatically. Then you have mass transfer cycles.
Where material actually moves between different parts of the Earth system.
Precisely. And those parts, those holding places for material, we call reservoirs.
Like the oceans, the atmosphere, the rocks themselves.
Living things, too, all reservoirs.
And material doesn't stay in one reservoir forever. It moves.
Right. And the average time it spends in one reservoir is called its residence time.
Which can vary a lot, like we said with the rocks. Some short, some incredibly long.
Exactly. Water might evaporate from the ocean, rain down on land, and flow back to the ocean relatively quickly. Short residence time in the atmosphere or rivers. But an atom in a deep crustal rock might stay there for hundreds of millions of years.
Okay. The material also distinguishes between geochemical and biogeochemical cycles. What's the difference there?
Basically, geochemical cycles are driven primarily by physical and chemical processes. Heat, pressure, reactions, transport without a major direct role for life. Think of shale turning into schist deep underground.
Mostly physics and chemistry.
Yeah. Biogeochemical cycles, though, involve life directly and significantly. Biological processes are key parts of the cycle.
So where does the rock cycle fit? Is it geo or biogeo?
Well, it's interestingly both.
Both. How so?
The deep burial, the metamorphism, the melting, that's largely geochemical.
Right.
But think about weathering. Life plays a huge role, like we said.
Right, the oxygen, the tree roots.
And think about sedimentary rocks like limestone, often made of shells from marine organisms, right? They took dissolved elements originating from weathered rocks out of the seawater to build those shells. That's biology directly involved in rock formation.
Ah, I see. So the rock cycle has components of both. It bridges the gap.
It really does. And it connects to other big cycles, too, like the water cycle, the hydrological cycle, which is all about moving water around, and the carbon cycle, moving carbon between the atmosphere, oceans, life, and rocks. We'll likely explore those more later.
It really paints this picture of Earth as this complex, dynamic system, everything linked. And looking back at what we set out to do today, I think we've hit all the points. We understand now why surface rocks change, why younger rocks are more common there.
Yep, covered the different pathways, the role of plate tectonics.
The energy sources driving it, how it fits into the bigger picture of Earth cycles. We've really unpacked it.
Absolutely. We've seen how this constant transformation is driven by Earth's internal and external energy, gravity, life.
Yeah.
It's all connected.
So we started by challenging that idea of rocks being permanent, and I think we've shown they're anything but. They're constantly in flux, transformed by this incredible rock cycle.
A continuous process, yeah.
Driven by internal heat, solar energy, gravity, life, highlighting how interconnected Earth systems truly are. We've covered the core ideas, the processes, looked at how diagrams like figure C.1 and C.2 illustrate this. We've touched on real-world examples, the geotours links Hawaii, the Appalachians, collisions, ridges.
And understanding how rocks form in different settings, that geology at a glance idea, Gives us that hands-on feel for how the cycle works in practice.
Definitely. We've covered the whole chapter, really getting to the heart of this fundamental concept.
No doubt about it.
So next time you see a rock, any rock, a pebble, a mountain, maybe pause and think about the incredible journey it might have taken and where it might be heading next in this endless cycle. It's kind of mind-bending, isn't it? And it makes you wonder, if rocks are constantly being recycled, what other things around us that seem totally stable are actually undergoing their own slow, continuous transformations we just don't see? Something to chew on.